Hello and welcome to Autodesk Simulation TV. My name is Mike Fiedler, one of the Enterprise Support Specialists here at Autodesk. Today we're going to be looking at Simulation in Action, AutoCAD and Simulation Mechanical Interoperability in the broader category of Design and Validation. So the description, what are we going to do today in greater detail? This demonstration is going to look at how we can utilize geometry that we create within the AutoCAD environment to produce analyses which will provide insight into the performance of our design. So beginning in AutoCAD Mechanical, we will then take the model that we have there, move it into the Autodesk Simulation Mechanical or Multiphysics environments. Anything we're going to do today can be done in Mechanical or Multiphysics. And then take a look at that. Once we apply some loads, some constraints, some properties to that model, do we want to change that design at all? Do we want to completely change it, make it look something completely different? Do we want to lengthen it? Do we want to shorten it? And so on. So what we're going to look at as far as objectives, how do we use AutoCAD line drawings to create line-based FEA elements or finite element analyses? Well, within Simulation Mechanical and Multiphysics, there are numerous element types that you can use. Some of those are based on a simple line. Those include trusses, beams, springs, rigids. So just there we list 4 different elements that are all based on a line. Once we get into the Simulation Mechanical and Multiphysics environment, you'll see that once I have that line geometry inside the analysis package, then I can give it specific properties that a truss needs, such as its cross-sectional area, or if I'm using a beam, I get more detailed and say it's a round section or rectangular section. If I were doing something like a spring, then all I need to do is tell it what's its axial stiffness or torsional stiffness. So all these different element types just beginning with a simple line. And then below that, how do we utilize AutoCAD areas or regions to create planar FEA elements? And again, you see that I've listed some different elements that are all planar elements. So if I begin with a enclosed region in AutoCAD, just envision a simple square, and I bring that into the simulation product, what I can do is mesh that region. Once I have that planar region meshed, then I can define it as 2D elements which say, what am I doing as far as translation in the Y direction or the Z direction? I can get into plate elements. Plate elements have a little more flexibility. Translations in X, Y, and Z as well as rotations. Shells, if I'm getting into mechanical event simulation, are very similar to plates. And then membrane for like fabric elements. Also, what are your loading and constraint considerations once you get into the simulation environment? What about analyses types? We're going to take a look at both a static and a mechanical event / nonlinear analysis in this presentation, and then ultimately how to review your results. Also down here I have a pretty long link. I'll step out of the way for a minute so you can see that. I just note here, probably useful to review the documentation on importing CAD wireframes. I would say the simplest thing to do when you open up the simulation environment, if you go into the Getting Started and then access the wiki help, if you just type in the keyword in your search of AutoCAD, you'll get to this particular link here, and this will give you some greater detail as far as what we can import, working with those models and so forth. But we're going to cover a lot of it here today, but in addition it probably wouldn't hurt to take a look at what's available on the wiki. So just to get started here, taking a look at AutoCAD Mechanical, and the very first model that I did here, just a simple truss or beam frame, and I'm picturing something like a pedestrian bridge here. So the railing that you might see on a pedestrian bridge, in fact there's a park pretty close to my house which gave me the idea or the inspiration for this model. So I've already created this model ahead of time, and now we want to do some analysis on it. What sort of different cross sections can we utilize on it? What sort of loads and constraints might we have? And how well does the model withstand those loads given that particular geometry? So going over to the Simulation Multiphysics, just launch Simulation Multiphysics or Mechanical. Again, anything we do here today, I'm going to be using Multiphysics, but it would apply in Mechanical just as well. When you open up the program, you're going to get this open dialog box here. And then if I scroll down to the types of files that I can open, you can see there's a bunch of different simulation files. So if you've already done a model, of course, and you want to reopen it, that would be up top there. And then coming on down, there's a little break up here, and then the different types of CAD files. And the AutoCAD DWG file is the second one in the list there, or excuse me, the first one under CAD files that you can open up. And then also you'll see Inventor files, Fusion files, CATIA files. So there's a big old list of files that you can open. Today we're focused on the AutoCAD models. So I'm going to choose AutoCAD DWG. And there you can see the two different models that I have prepped for today's presentation. I'm not going to just double click or click that file and say open. I'm going to click it, and then we're going to talk about some additional things. Before I go ahead and open that file, when I choose the DWG file, there's an options button here that you should be aware of. So let me go ahead and click on options. And these options are going to be available if you're importing a DWG file, or an IGES wireframe would be very similar to it. So first of all, looking at this dialog box, it says if both exist, what do you want to import the model as? Do you want to import it as a wireframe or as a 3D surface or solid? Again, what we have, we're starting with just a line model. So that line model is going to represent the railings of this pedestrian bridge. So I have wireframe chosen. And then right below that, wireframe options. I have the box checked and it says drawing is a 2D model or planar model, and what plane is it drawn in? I have noted here that it is drawn in the XY plane. That becomes more important with the next model that we open up. We'll expand upon it a little bit there, which clues me that I do not need the next option, which was transform to the YZ for 2D elements. We're not doing 2D elements, we're just doing lines in this case. So I do not need that one. What I do need is the next checkbox. It says import the lines, arcs, or curves as mesh lines. So what I want to do is take these lines that we have drawn in AutoCAD, and I want to transform them, or convert them really to a simulation model where those lines from AutoCAD become line elements within the finite element analysis. So either trusses or beams or springs, something that I'm going to define. So I'll go ahead and click that checkbox. And then notice right below that it says arc divisions, and then by default it's set to 4. So if you do have some curved geometry in your AutoCAD drawing, a circle or an arc, and you're going to convert it into line elements or segments, think of springs within the simulation environment, then we're going to divide it into a number of line segments. Default there is 4. In this particular case, I don't have anything that I need to worry about there as far as arcs are concerned, but I do want to convert them or bring them in as mesh lines. Going on down the list here, towards the bottom there, you'll notice replace invalid part IDs with a part number 255. So when it doesn't understand or cannot associate a specific part within AutoCAD, it's going to make that part number 255 within simulation. So just be aware of that. Once the part opens up within the simulation environment here, if you see things on part number 255 or surface or layer, it just wasn't able to associate it to a specific part, layer, or surface number from AutoCAD. We'll talk about that a bit more in just a second. I'm going to say OK and OK. Now the next screen here is just asking me for what unit system I want this model to be in. I've drawn it in inches in AutoCAD, so I'm going to be consistent and use the English inch unit system here in simulation. The next thing that it's asking for is it's coming in, it's just about in here, is what sort of analysis type do I want to utilize? For this bridge, we're just going to do a simple linear analysis, and under linear, you'll notice you have a whole bunch of different analysis types you can choose here, a static stress. Perhaps you want to do a modal analysis here, see what frequencies it is really sensitive to. You have a different grouping of vibration analysis here, response spectrum, random vibration, frequency response. We're just going to do a static stress to begin with on this model. We'll say OK. All right, so there is our model. Let me orient it a little bit better here so we can view it as I had intended the orientation. Okay, so there is our model, and you'll notice that as this model comes in, it is in the menu tree over here, part number 1. That is defined in the wiki help that I pointed out a little bit earlier, but just to be a little more specific about what it's doing, the AutoCAD layer number becomes the part number within simulation. So when I first went into AutoCAD, I have to be honest here, wasn't really paying attention to the layer that I was on, drew the whole thing up, brought it in the simulation, didn't recognize that layer number that it had chosen, so it set it to a part number 255 within simulation. That's okay. I could have run it as part number 255. Likewise, in simulation, there is a way to select those lines and edit them. You can change them to a different part number, surface number, or layer number. I can show you that. In fact, we will do that for this model. But what I wanted to do was to show you that if we put it on layer number 1 within AutoCAD, it ends up being part number 1 here within the simulation environment. And that is, in fact, what we have. So the layer number in AutoCAD becomes your part number in simulation. In a similar fashion, the color number within AutoCAD becomes your surface number in simulation. The surface number, if I expand, you'll see there's part number 1. If I expand the plus sign next to surfaces, that shows me all the different surface numbers that I have in my geometry. And here, that is also set to surface number 1. This particular model we're going to treat as a beam model. So for beams, let's talk about the part number, the surface number, and then the third thing within simulation would be the layer number. So the parts, when do you need different part numbers? Primarily for part, underneath that is the material. So anytime that you have different materials, you'd want to have different parts. So if I wanted the horizontal sections to be one material, then I would make those one part. And then if I wanted the diagonal members to be some different material, then I would set those to a different part number. So I could say part number 1, here's your material, and then further down the menu tree, part number 2, and here's what your material is. So again, let's keep the discussion specific to beam elements. It's a little bit different with different elements. For the most part though, part number, anytime you need to change material. That one is pretty standard across. In fact, let's go ahead and define our element type now. When I right click on the element type, there you can see the various element types that it's exposing for me. I could make them truss elements. And again, truss would work for this model just as well. You define the cross-sectional area. So if you're just trying to get a kind of a broad picture or a big picture of what's happening, right below that is the beam, which I'm going to utilize. I like the beam a little bit better. They're good for long or short members, plus you get to define what the cross-section is, the cross-sectional properties, so you can give it a little more detail. And then there's your membrane for fabric, bricks, plates, tetrahedron, on down the list. So I'm going to make them beam elements. And then if I go into the element definition screen, the next item down, just defining all the elements that are red over here in the menu tree. If I go on down, you'll see there's the element definition screen, and it's looking for the sectional properties. Right now, you'll notice that it says layer number 1. So there is only one layer in my geometry. My geometry is one part number, all the lines are the same layer number, and all the lines are the same surface number. The layer is, as you can tell from this, what controls how many sectional properties I can define in my model. So as many different layers as I have the lines on, that's how many different cross sections that I can utilize. In this model, I'd like to use 2 different cross sections. I'd like the horizontal members to be one thing, and I'd like the diagonal members to be another. So I'm going to go modify this model so I can change its attributes and add another layer in here. I'm going to cancel out of the element definition for now, and I'm going to go into a point select command in conjunction with selecting lines. Just select one line. I'm going to hold my control key down so that I can select all the diagonal members. And then how do we edit the attributes, either the part number, surface, or layer? I right click and I say edit attributes, and here comes the dialog screen, and I can just type in its new part number, surface, or layer number. So I'm going to change the layer number, and I'm going to put those on layer number 2. So layer 1 is my horizontal, layer 2 is my diagonal. Now the surface number also has applicability for beam elements. That controls the orientation. What is the y axis of the beam? For what I'm using here, surface number 1 corresponds to the y axis being aligned with the global y-axis of my mini-axis. So you can see x is horizontal, y is vertical. So that'll work just fine for our model. You might need to change it in other models. It's no big deal. You just select the lines, change your surface number. So surface 1 does one thing, surface 2 goes to the next axis, surface 3 goes to the next axis, and so on. Let me go ahead and say OK to layer number 2. Now I'm going to go back into the element definition screen. And when I go into the element definition screen, you can see that we have 2 rows there, 1 for the horizontals, 2 for the diagonals. So what about putting in the section properties? Of course, you could open up your AISC manual and you could look up that particular section. You could type in its properties. There's an easier way to do it though. If I click in any one of the fields, say for row 1 or layer 1, then the cross-section libraries button becomes available. So I'll go ahead and click that. And then I have some options here. From the left-hand side, if I go to a pull-down menu, you'll see there's AISC 2001, 2005, Rev 9, Rev 8, etc. So I can choose an AISC manual and then pull the section type from there. Or in the upper right-hand corner, which I'm going to do, I can select some simple sections. So I have round, pipe, rectangular, hollow rectangular, etc. I'm going to choose a hollow rectangular for the horizontal members. And base 1, I'm going to make, say, 1 inch. And base 2, I'm going to make, that's the inner dimension on the base, I'm going to make that a 1/2 inch. So we have, what, 1/4 inch walls. And then for the height, I'm going to make that 3 inches high. So the inner wall is going to be 2.5 inches. Once I say OK, that updates all the properties for me. Let's take care of the diagonal members, cross-section libraries. We're going to make that a round, and I'm going to give it a radius of 0.5. OK, so there's all the sectional properties. Next thing I need to do is the material. So I'm just going to say Edit Material. And we'll make this A36. OK. You'll notice some blue dots on here. These are construction vertices coming over from AutoCAD, the endpoints of the lines. I'm going to turn those off just to make the model a little bit clearer for me. So on the View tab, I'm just going to deselect construction vertices. OK, now what we have to do yet would be the boundary conditions and the force on the model. So I'm going to take the extreme left-hand bottom end of the model. Again, I'm going to go to Selection. I want to do a point select. This time I want to select vertices. So I just want to select an individual location or point. So I'm going to say Select Vertice. And when I have that vertex selected, I can right-click and choose Add. Under my Add menu, there's my options for my constraints and my loads. So I'm going to do a nodal general constraint there, which will make that node fixed. When I choose fixed, I choose the preset button of fixed. Notice that it's stopping translation X, Y, and Z as well as rotation X, Y, Z at that node. And of course, you can check and uncheck boxes just so you can release whatever degrees of freedom you need to have released, whether it's a rotation or a translation. I'm going to make that end completely fixed. Over here at the bottom right-hand side, we're going to say we have another constraint right there. Right-click, Add Nodal General Constraint. In this case, I'm going to do fixed, but then I'm going to free up TX as if it's on some ruler. Again, let me move away so you can see the mini axis. So there, the horizontal is the X direction, so I'm allowing it to move in the X direction. And then also on that ruler, I'm going to say that you're allowed to rotate about the Z axis. So I'll uncheck RZ. OK? So that will be the constraints for my model. We're just saying it's supported at the two different ends. But of course, anywhere where I have a node on the model or a vertex on the model, I can apply some sort of constraint there. So if you had a pillar here that was supporting it, just maybe in the TY direction, maybe I have another ruler right here helping to give it some sort of constraint. Again, you could add those onto the model. All right, so for our force, I'm just going to take a single node here, top center of the model, and adding a force in, we right-click, we say Add Nodal Force, and the magnitude of our force is going to be minus 1,000 pounds in the Y direction. We'll say OK. All right, so the last thing that I'm going to do before we execute this model is I'm going to break it into smaller divisions. The only reason for doing that, understandably, this geometry that we have here, the lines here are representative of our geometry. But when we go to run the analyses, the loads are always at the nodes of the model. So if I apply gravity to this model, as we execute the analysis, a portion of the gravity gets applied to this node, applied to this node, that node, and so forth. So if I break this model into smaller line segments, then I can see deflection better. It approximates the deflection better. That load is distributed a little more uniformly over the model. So before I execute any beam model, I'm just going to select the whole thing here. I need to be in a select line. Let me select all the lines on the model. And how do we divide? We right click and we choose divide. And I'm going to set it to 4 segments. So I'm breaking each current individual line segment into 4 smaller segments. We'll say OK. And at that point, let me just click a line so you can see that they've been broken up into smaller segments. There we go. And we'll execute the analysis. Analysis, run simulation. And this is going to run fairly fast. Not too many elements there. Okay, so there's 8 seconds or so in the analysis. When it comes into the results environment, now I can see my model. It also visualizes the geometry, so I can see those hollow rectangular sections. I can see the round sections that I utilized on the diagonal members. And the default result is displacement. So we can see we have about 0.007 inches of displacement, so pretty small displacement on it. If I rotate the model around here a little bit, let me zoom in a little bit so you can see the rectangular section there and the round section. Helps if I move out of the way. Also of interest to you would probably be the stress results in the model, of course. So from there we could go to beam and truss, and let's say that we look at axial stress. So when you look at a lot of different beam results under the beam and truss results menu, you'll get a high and a low value. So here we can see 865 at the top of the legend box, corresponding to this member, which tells me that's in tension. But then you also need to look at the negative end, which would be your compression. And I can see that I have about a minus 900 in compression. If you're looking at that model and wondering why it's deformed so much when we only have 0.007 or 0.007 inches of displacement, 0.007 inches of displacement, we do exaggerate the displacements by default in linear static stress. So just to show you where we can toggle that, if I go under Show Displaced and choose Displaced Options, you'll notice if I click on As an Absolute Value here, the scaling factor is 835 times the true display shape. So if I want to see the true display shape, absolute value of 1, and I can hit Enter. And of course, the displacement then is so small that I'm not really going to see the trend or the direction of the displacement. So I can magnify that. There's 1,000 times. Okay? So based on that, very simple to bring in the line model, define the element type, give it some properties, load and constraint, and now we can see what are our deflections, what are our stresses, and based on that I might make some judgment. We had very low stresses in the model, we had very small displacement in the model, so I know from that that I can probably change the sections that I'm using, or if somebody was hoping that we could make the pedestrian bridge a little bit longer, even between these two supports, I think you could safely get away with that. And then go ahead and make the changes to the model, re-execute the analysis, and see how the new design works.